Hi, everyone. This is going to be our second lecture on our series of lectures on linear algebraic groups. This time, we're going to be covering the ideal map, this I map. Now, our previous lecture, we ended with mentioning that every affine variety would be the intersection of finitely many hypersurfaces. And recall last time we were talking about our introduction just to varieties and zero sets in general, and this Z map that we had. So now we're looking at a different mapping here. So let's go on. Let's take V to be an affine variety. If we have any affine variety, there might be many ideals I such that we take this variety and it's equal to the zero set of just some ideal I. So just to give ourselves an example, let's say we're taking affine 2 space and we're going over the real numbers. We could see that the y-axis itself would be the locus of the ideal that's generated by x of taking the polynomial ring with real coefficients and two variables x and y. But it also would be the locus of the ideal generated by x squared or x cubed, and so on and so forth. So more generally, the zeros of any polynomial are going to be the same as zeros of all of its positive powers. So it follows from here that the zero set of one ideal is also going to be equal to the zero set of an ideal to some k power for any k that's greater than or equal to 1. And these are integer powers, of course. And now, if we just think about this for a moment, this should be intuitive to what we've seen in a basic pre-calculus course, right? If we had a 0 of one polynomial and we just took it to some positive power, it's not like we've lost a 0 in any way, right? Still have that same exact 0. It just might be at a higher multiplicity, but in here, we're just looking at the zeros of the polynomial, right? We're not really necessarily concerned about multiplicities. Now, if we have an ideal whose zero set determines a particular variety, it might not be unique. There is going to be a unique largest ideal that will determine the variety, and this will be given by the set of all polynomials that vanish on the variety V. So this is how we're going to define this. In general, if we take any subset A of an affine n space, we can define this I of A, so this little fancy I, and this is going to be taking polynomials that are in a polynomial ring just from some field K and n indeterminants. And this is going to be described such that if we take this polynomial, we take polynomials F, where if we take points that are in our subset, so A1 through AN in our subset of our affine n space, then this is going to give us 0. So just all the polynomials described in this way. Doing this will mean that this I of A would be an ideal, and it's going to be the largest unique ideal of functions that are identically 0 on A. So this kind of prevents us from that little issue we saw before where, we have so many ideals that could generate, one zero set. This way we have a way to give ourselves a unique ideal. So just kind of think about this idea for just a second. All right. So now we can think about this and realize that this will give us some correspondence here. So this I map is going to take us from subsets in our affine n space, and they're going to map to ideals that are in a coordinate ring. And then if we want to think about last time, we saw this other correspondence with this zero map, the Z map, right? Where we were taking ideals of a coordinate ring, and in this case, we're generally taking our k to be C, the complex numbers, and it was going to be mapped to an affine variety in our affine n space. So it's kind of going one way, and then this is kind of the opposite direction, right? And soon we're going to kind of see a relation between these two mappings. So let's look at some examples. Let's say if we're thinking about the Euclidean plane, this I would be the x-axis itself. So this would be the ideal that's generated by y, that's in this coordinate ring. Real coefficients, two variables, right, x and y. So if we just think about the x-axis itself, that would be that ideal generated by y here. And that kind of makes sense if you just sit there and try to think about it for yourself for a second, just from what we know from our basic pre-calculus courses. Second, let's take a field, some field K, just an arbitrary field. if we take the ideal of functions that are vanishing at these points in our affine n space, so just a1 through an, this is going to be maximal because it's going to be the kernel of a surjective ring homomorphism. This is going to take us from our polynomial ring with coefficients from k and indeterminates. It's just going to map back to that field k given by evaluation at these points in our affine n space. So our I that we have, that fancy I, it's going to be taking all these points in our affine n space. And we can just define this to just basically be taking all the individual indeterminates here, and it'd just be taking like the xi's minus the ai's up to however many, indeterminates you have in this case. So if you need additional examples of this idea to how we've kind of set this up, you can go to page 660 of Dummin and Foote's algebra textbook. It's a pretty good reference for this idea. It helps you out if you are really struggling to grasp this context. But I think this kind of gives just the basic framework of it that most of you with some background should be familiar with. Okay, so now let's look at just some of the properties of this I mapping. So let's say we take A and B just to be subsets of our affine n space. The first property would just be that if A is a subset of B, then the ideal map of B is going to be a subset of the ideal map of A. So just like that zero set map that we had, that Z, this is also going to be contravariant. Second, if we take the ideal mapping of the union of these two subsets, A union with B, then this would be equal to taking the ideal map of A and intersecting it with the ideal map of B. You might have to play with this a little bit to make it make sense in your head, but these properties definitely hold. You can check them for yourself. The third one is if we take the ideal map of the empty set, it's going to give us back the entire polynomial ring that we had in our arbitrary field with n indeterminates that we're using. So to map whatever the affine n space that we're using. And then if we have k to just being infinite itself, well, then the ideal map of the entire affine n space itself would just be 0. So now we can kind of move on to some of the relations between these two maps, like the Z map and the I map that we have. So the first one, if we take A as just some subset of affine n space, then A itself will be a subset of that Z map, the zero set map, of this I mapping of A. So sit here, pause for a second, think about this. And more generally, if we take I itself as just an arbitrary ideal, then that would imply that I itself is a subset of the ideal map of the zero set of I. The second property is if we have some variety that's just defined to being zero set of an ideal, and this is an affine variety, then that variety V is going to be the zero set of the ideal mapping of the variety V itself. So it kind of just spits back the variety to you. And if you take an ideal I itself to just be the ideal mapping of that subset A in affine n space, well, then the ideal mapping of the zero set of that ideal I would just give us back I. So we can kind of just sit here and look at this relation that you have for the technicalities, but the general idea is that if you're taking the zero set of I, or sorry, if you're taking just the zero map Z and you're taking the ideal map I, they're going to be inverses of one another as long as they're restricted to the collection of affine varieties where V is equal to the zero set of some ideal I in affine n space and to the set of ideals in the coordinate ring of our affine n space that are of the form the ideal mapping of that variety V. So let's make this a little bit less abstract, and we can look at like a concrete example of how this would apply in something that we've just seen in, maybe a Calculus 3 course. So let's say we're working in R3, okay? We're going to take the bottom half of the cone that's in R3, and we're going to define it by the equation x squared plus y squared is equal to negative z. If we take this cone and we intersect it with any plane, just an arbitrary plane equation, say ax plus by plus cz is equal to d, where, a, b, c, and z, these are just constants, right? They're just real constants. And now this is going to give us an ideal that's generated by these two polynomials. So for the variety that we get from this intersection, it's actually just going to be either a circle, ellipse, a parabola, a hyperbola, just depending on how we define our plane, because that's going to define that intersection itself. So to kind of illustrate this idea, we have this diagram that's just pulled from Wikipedia under conic sections. But we have to keep in mind that we're actually just taking the boundaries in this image. So not these whole, the whole colored area itself, but just the boundary of that colored image. So you can see if you have, one plane going that's kind of just horizontally, we would get a circle when we intersect it. And then depending on like how we've had some sort of slant on the plane that intersects it, we could either get an ellipse, a parabola, or a hyperbola. So effectively that kind of boundary that we're getting here is just determined on how we've moved this plane around to intersect this cone. So if we were to kind of use these definitions that we had above previously, we would kind of get this following, that subset of the affine n space that we have, that A, it's going to be the curve that we obtain by the intersection. So that's just going to be either the circle, the ellipse, the parabola, or the hyperbola. And then here, also the ideal I, then it would just be the two separate hypersurfaces. So it's defined now by two equations. So we have the cones equation and the planes equations. So we can define I to just be taking x squared plus y squared plus z. And then also by taking that planar equation ax plus by plus cz minus d. So the idea here is, right, normally these equations are set as like some equivalents, and we've kind of moved everything to one side, set it to 0. That's how we define it here in this ideal I, right? We're just looking at everything that we have here, setting up this way. And then thirdly, the way that we're defining that variety V, it's going to be the 0 set of this I that we just defined above, this ideal from above, where we're just looking at those two separate hypersurfaces. So this relationship is just going to hold, this relationship is going to hold. Try to think about this for a second. It's not necessarily, it might take you some time, but it won't be too difficult, I think, for most of you. You just have to kind of sit there, pause with it, play with it a little bit. But once you've done that, it should make where you go back to these arbitrary definitions that we have with these two relations. You can kind of sit there, play with it yourself, and kind of see how this all is going to, hold together. And that's gonna conclude everything that we're covering on this section. Thank you all for watching, and we'll see you in the next video.